we start the lesson? The
okay.
class?
Are you here? And are you ready?
Yes, thank you.
Okay, I will try to keep my chat window here to see what questions will be online. I'm trying to type all the texts, but it will require more than 40 minutes. So I will show how it looks like and explain why it should be this should be created this way.
One
Okay?
moment only. Abraham, is this recorded?
Yes.
Are we recording?
It's still recording.
Perfect. Go ahead, Ilya.
Okay. Okay. So can you see me?
Yes.
Can you see my screen? Okay, yes. Let's start. So we want to create a fourth CPU. You may contact me. I put my email here, so I'm open to some kind of collaboration and questions and just discussing. No problem. I like it. Okay. What I plan to do now,
The screen stopped.
I don't plan to promote Ford or promote my. So Ford CPU is my previous meeting was a Ford for everywhere. Now it's Ford CPU for everyone. So I plan to explain how you can use FPGA, Verilog, or maybe VHDL to describe your own CPU. Of course, it's not the smartest one, but it has all properties and features of stack CPU capable to run Ford. I already sent my project files. It's for Xilinx Vivado CID, but I didn't use any Xilinx specific features, so you can retarget to Altera Intel or to Lattice for microsemi, whatever. And I don't ask you to follow me. I don't ask you to follow my GitHub projects or something else. I want you to follow your vision and goals. Okay, what is CPU? We cannot understand almost nothing from drawings. We usually can see on the schemes of CPUs, MCUs, and so on. We can see some components, they are connected by buses, but we cannot see process, and we cannot understand what we need to describe in our schematic.
Sorry, can I ask people to mute the video, please?
Sorry?
Can you ask people to mute their microphones, please? Thank you.
Okay. Okay. Modern digital electronics is synchronous. This means it uses clock signal. It is very important from approximately 19 nanometers or less, because previous generation of FPGAs and ASICs use mixed schematics with strobe and clock signals. Now it's clocked. So we can draw very simple scheme with memory and some digital electronics connected to it. So we have front edge of clock signal, and every time at this edge, we are reading command from the program memory. So at the start, we have program counter equal to 0. We will read command addressed by this 0, and at the next clock, we can execute. While executing, we will change program counter. Okay, now it is equal to 1, and so on, so on, so on. So we have a simplest pipeline, but CPU is not pipeline yet, because we have two cycle CPU. What is it's a cycle again, so it's not a pipeline. It's not a pipeline. To read command, we need to type literally this line. So command is memory content addressed by PC. So at the next cycle, we need to perform switch operator based on the command value. It's very simple so far. Okay, how pipeline can work? We know where most processors runs programs sequentially. So most probably, next command will be executed from the next address. And while executing current command, we can fetch next command. The only problem, we can jump. We can perform jump or conditional jump with condition when conditional is true. We can perform calling subroutine, and next address will be not incremented by one. Okay, this is obvious. So we need, in this case, we need to discard next command we just read. So we need a kind of special flag indicating is next command is right, or we don't need to execute. There is an approach existing in current CPU designs when command just read is executed too, but this is more complex for compiler designers. So commonly used three-stage pipeline works like you can see on this slide. So first cycle, we have PC, and at the clock edge, we will read command. We have a huge register file. Somewhere our operands are located. So we can use, for example, register number 3 and number 5, and this is determined by special fields in our command. Okay, this is no stack CPU so far, but at the next cycle, we need to decode commands. So we need to write to special registers two operands. We cannot do it at the first cycle because we still don't know which registers are our operands. And third cycle is to execute and to write results to the register, which is determined by destination. We can pipeline it. We can pipeline again. This is a very commonly used pipeline for free stage, like maybe minor ARM, not Cortex-A, but many CPU designs today are free stage. Two-stage pipeline is available for stack CPU because we know our operands. They are always on the top of stack. So while we are fetching our command, we can put to operand registers two top values on the stack. So we have an objective feature of stack CPU. This is 0 operand. We don't need to determine from the command value which operands we are used for current command. Okay. So we can go now to project design. I suggest to use this architecture. I suggest to use two-cycle, two-stage pipeline with 2 cycles for every command, and with one clock penalty when we break the sequential execution. What do we need? We need Xilinx Vivado. It's a complete design flow from the schematic input, RTL, so VHDL or Verilog. We can use both mainstream language. We can use almost any FPGA board. I have digital data board. It's low cost, and I when I measure the size of my 32-bit CPU, it took less than 2% of FPGA size. So it's very small. Okay. The first thing we need to do with any FPGA project, it's very important. It's about 1/3 of engineers. Sorry, what is, okay. What we need to do when we're moving from simulating to real hardware, we need to set up clock generator. It's very, very important. This is driving how DCM or maybe PLA N7 serial, so maybe mixed mode clock manager should be installed to our project. And this is driving from real Xilinx FPGA device. We can see this feedback is very short, but in reality, buffer for global clock network is installed at the center of FPGA. Clock feedback is running back to mixed mode clock manager. And real signals are not ideally fits into our simulation. So we can put, for example, 100 megahertz. If we enter this signal from the edge of our chip, we will see cycle waves of edge of clock signal throughout our FPGA. This is very bad. We will meet clock racing. We will meet very unstable behavioral, but our simulation will not show this. So this is maybe it's not so easy to do for FPGA beginners, but every time we are going to real FPGA board, we need to set up clock generator. It's very, very important. From my experience, it's more than 10 years of providing Xilinx lectures in Russia. About 1/5 of engineers missed this point. Okay, what's next? Well, we can use IP Core Wizard. This is very simple indeed, and CID tools will provide us with a simple Verilog installation. So we have our component. This is Clock Wizard 0, and we will connect our input signal of our project, and output of clock generator will be connected to our global clock signal of our CPU. Okay, we need to do this. This is very important. Okay, for CPU at last. It's very common to software designer to describe how CPU is performing actions to provide behavioral of fault primitives. In reality, this looks like wrong way. We don't describe actions. We describe components, connection in our project. When we connect it, we cannot provide a sequential behavior. It will be last forever. So when we connect, for example, AND gate, it will be connected forever. So we need to describe actions for every register of our CPU at every clock edge. This is very easy indeed. Okay. In our design, we have program counter, of course. We always need a program counter. We have one register for return stack. I didn't implement stack for returning address because there are trade-offs and many options to use registers or to use memory. I will show it later. And this is a very good exercise to extend existing design. I will send to all of you to provide return stack of the size you want. Okay, we need state flag. So comment is not ready when it's 0, or comment is okay when it's set to 1. Okay, this is what I told before. Some comments breaking the sequential execution must reset with state flag. It's only 1 bit. Okay, we have data stack. We have data stack, and we have depth register. Depth register will directly provide 2 numbers from stack to arithmetic logic unit. And this is not synchronized component. So all rectangles are registers, and this is not register. Okay, we have data memory with address, data, and write enable, right? And we have program memory with program counter input, with command output, and we need to add external address and data lines to prevent very, very high level of optimization. If we fill our program memory with zeros, with no chance to change it, our synthesizer and FPGA tools will optimize it away. Absolutely. And we will receive a design which is able to execute only zeros, so no hardware is required for it. Or maybe we fix a program, we will receive a design for only this program. It will be read-only memory, so no change to modify, and synthesizer, of course, will see this and will optimize. We don't want it. We want to keep all of this hardware. So what we need to do next? We need to describe every input, every signal of every component we use as our register model of our CPU. Okay, control flow is very easy. We need to provide state, and we need to provide PC. So at reset and at startup, we need to fill all our registered by zeros. This is done for PC, this is done for state, and this is done for depth. Okay, this is literally code. I will show it later in my Xilinx Vivado. Okay, we just set reset. What happens? It's very, very easy. We will write new state to state. I can show it again. All of this is done at the positive edge of clock signal. We need to write new PC to PC. And if our comment is okay, if we don't jump to another address, we need to write new depth value. So we always providing PC and state because it's control flow. But if our comment is wrong, we just jump over it. We don't need to execute next command and apply all its effects. We only need to provide state and PC. Okay. I carry to previous slide. We just provide PC, state, and depth. Okay, what's next? Next, we need to create some kind of our comments. It's a common trick to use defines, not to try to use constants, not to try to use numbers in our code, because we can change our command designation and we will forget it, of course. So we can use it this way. For example, we will use 0 for no operation. We will use 1 for fetching. We can use, we cannot use this sign because it's not supported by Verilog. So we use alphabetical and numbers, and so on, so on, so on. I will show how it will look. Okay, how to determine UPC? What we can do? We can jump, or we can call. In our very simple CPU pipeline, we have no option to read operands. We need provide operands first and use it, for example, from stack. So our jump command is not code for jump and some parameters after it, because we keeping this simplest architecture: fetch, execute, fetch, execute, fetch, execute, and pipeline. Yes. So when we try to jump to a new address, we need to know this number. So our jump and call are used top stack value. Okay. I don't want to think about many kinds of conditional jumps. We are trying to create fourth CPU. Fourth CPU has if fourth. It will jump to something forward, yes? If top number at the stack is 0. So if condition is true, we will continue, yes? Otherwise, we are jumping somewhere forward. Okay, it's easy. We don't need to work with flags, a carry flag, 0 flag, less, maybe sign, maybe overflow. We don't need to follow common CPU templates. We are trying to create for CPU with tightly coupled hardware and software. So many of our commands will have a direct support in our CPU hardware. Okay, return. Now we can use only one level of subroutine calls. Later, this may be replaced. It is easy. We need to draw stack here and perform some kind of modification. I just show you. Okay, new state. New state. We have two options. Of course, when we perform resetting, new state is 0. Our command is not ready just after reset. We need to read it. Okay. Conditions when we break our linear sequence are, first of all, state is 1. So it's true command. It's not a tail of a command we trying to jump over. So state must be 1. And maybe it's jump, maybe it is call, maybe it is return, or maybe it is if command and we are really jump to a new address. So we have 4 real situations when we will break our linear execution. If we will add any other command, for example, jump with another condition, jump with another command, jump by the table, we need to modify new state logic. Okay. Okay. Return. At reset, we need to write 0. It's easy. And if state is 1, so it's not discarded command, and command is a call, we are writing current PC to return register. Okay, this is easy again. That's almost all. Our program memory. This is a 2-dimensional array. We are describing program. It's our name of memory. We have 8K of cells. This may be any size you want upon FPGA you have at hand, and we can just refer to documentation files. What is the amount of memory we have? If FPGA is less, okay, it will be, for example, 1K or maybe a half of kilobytes. And every cell of our memory array, it's a register. It's 8-bit register. So description is very simple too. This is a line you've seen before. And this line is additional line. We just have no such time to explain how UART is working. But this is external signal going from simple UART controller. So when we have write enable program signal accepted, we will write a byte to this address. So it's very simple external interface to not to let synthesizers to optimize our program array. Okay, data stack. We have this description in Verilog. So we have, for example, 8 stack cells. Modify this and you can modify stack size. And every cell on our stack is 32 bits wide. Okay, looks better. And better. And better. So we are not MITs here to create 32-bit CPU. We can use any bit you want. What our stack will do at every positive edge of clock signal. If state is 1, if we want to write to stack, we will write result to stack. It's very easy again. So write to stack, state is for interior of our CPU. We have address of cell we want to write, and we have data to write. And this is clocked behavioral. And this is just multiplexers. So we are connecting to the stack A signal, the top of stack, and we connecting to stack B. It's up on you. I use A and B. Why not? So A, it's always a top of stack, and B, it's always a second top number. What is the logic? It's explaining very easy. For example, we have depth is equal to 2, and we have addressing of our stack cells. So 2 is an index of stack cell. We need to put a new number. Okay, so 2 is a new stack cell. Now it's free, and depth -1, it's top of stack. And depth -2, it's the second top. This is just a logic I use. You can rewrite it, but now we can see depth is equal to 2, and we have 2 cells of stack. Okay, now we need to describe all of this. This is our new depth logic, and this is some common architecture. I don't want how to name it. Of course, we can use a very free rules to assign numbers to Ford commands. But every Ford primitive will use its own stack effect. For example, codes from 0 to 15, it's no change for depth register. So it's like no operation, like fetching, like returning. So fetching, for example, read one number and puts one number. So it's replacing address by data from memory. Okay, so no change for that. Drop and over, and so on, so on, so on. Another number of stack. Plus and minus and or XOR, and so on, so on, so on. -1 cell on the depth on the stack, and we writing. So 2 numbers from stack and 1 number in exchange. Okay. Words like store, writing to port, if requires address and condition flag. So if will take two numbers. So I use a very simple grouping of for primitives by their effect on stack and on depth. Okay. Okay. We can analyze in this case only 4 high bits in our command. So from 16 to 31, it will be 1. Okay, 1 and 0, 0, 0, 1, and 4 bits for indicating which exact command in this group. Okay, new depth is depth plus 1. 2 or 3 minus 1, 4 minus 2, and all overs default is unchanged depth. Okay, again, we just described a new depth value. What about address to write? We can check it. When we need to put an hour number, we will put it on the depth register. So, okay, depth is 2, for example. We will write a result to second to the cell with index equal to depth. Okay. 2 or 3, we will write to depth minus 2. 4 again minus 2, and this is a special case. I will explain it now. This is for literals. And all over address is depth minus 1. So we are addressing the same cell, top of stack. We are addressing the top number. Okay. Write to stack. We have groups which are, for example, 4. That if store output, read 2 numbers from the stack and don't leave any result. So we can put write stack signal to 0 and no actions to write in any stack cell. And with only thing requires our attention. No operation, 0. This is in default group. So when we performing no operation, number with will replace the top number of the stack. We can describe a special case for this. We can split our groups. For example, we can perform some kind of architectural work. And for example, 0 with high bits, it's comment when no stack effect and no writing. And for example, 5, no stack depth change and write. It's up on you. Special case. Okay. We need to describe how results are obtained. We have stack A and stack B, and we can play with it. And of course, we need to put literals on the stack. There are many CPU courses, there are many tries to explain how to describe CPU, and all of them started with plus and minus and or, XOR, and so on. CPU must be able to jump, and CPU must be able to load numbers to registers. Otherwise, okay, we can add numbers, but we have no source for that numbers. There are many options indeed in CPUs and in stack CPU. This one I used for maybe my 4th CPU generations. This is very simple, and this not breaking the micro architecture we just implement. Okay, we have comments with from with 1 bit in 7th number. Okay, so from 128 and up to the end of byte. If so, 7 bits are representing a literal. So we need to connect 25 bits on the stack, shift it left, and concatenate with newly read 7 bits. This is bit format. This is with brackets is concatenation in Verilog. We need to combine a new literal on the stack with 25 old bits and 7 new bits. In this case, we are independent on the CPU data bit. With sequential shifting, we can load 32, we can load 64, and more and more and more. Moreover, if we can have, for example, a very short literal, which can fit into 7 bits, we can load it with only one command. And the only thing, this is a very little trick. We need a seed to extend literals. The first number on the stack must be placed by any command. So, for example, for our CPU design is literal 0 and literal 1. So when we execute these commands, and this is there are commands from our groups with stake effects, placing one number on the top of stack. So we have two options. We cannot -1, for example. We cannot oftenly use literals in this, so no problem. And okay, we can add numbers. We can read numbers from memory. We can read numbers from external signals. It's again, it's placeholder. We can read, for example, switches or buttons from our FPGA board. We can perform logical and not. We will need it. I will show. Of course, it's fourth CPU. We must describe that, otherwise it's not real fourth. And we can subtract numbers. Please take a notation. When comment is no operation, I note before, we will write something, and we will write the same value as the top of stack. Okay, this is some trick. So, block RAM in FPGA is a true pole static memory, and small effect is very common for static memory, not for stack CPU. For all CPUs we need. When we read value at the positive edge of clock, we will receive our value at the end of this memory model. And just on the output of memory, not directly in our top of stack. So we need another cycle to store data to the top of stack. So when we trying to define forward fetching value from the memory, we need to waste one cycle. So top of stack is connected to address of our memory. Every time, every clock cycle, according memory content will appear on the output of memory, and we will write it at the second cycle. It's not only stack CPU problem. Many CPUs implemented in FPGA or not has the same effect. So we cannot read value and write it to our register at the same cycle. Okay. Okay. We are going closer to our real example. We will write a binary counter. This is another snippet of Verilog code. So we can use this procedural operator, initial begin. It is useful for simulation, and it's also useful for filling FPGA memory by initial values. So it works both for simulation and implementation. Okay, we are placing seed at the top of stack. We are filling it. It's placeholders, so we can use large numbers, not with 7 bits only. So 0, 0, 0, and this number is high bit is set to 1, and our offset. So we want to jump to the address number 21. Okay, so just start up code. Jump to forward. We need a real delay, not just simulation, blinking, binary counter. We need to see LEDs. Okay, why 7 millions? Because I use 50 megahertz clock speed for this CPU design, and there are 7 cycles to perform every iteration. So 7 cycles multiplied by 7 millions, about 1 second pause. Okay, very simple. How we need to split it to our literal? I use calculator. I convert my 7 millions to binary representation and split by 7 bits. So seed, yes, seed 0. This is flag. 7 bits are literal, 1 and 1. So this number, this portion is here, this portion is here, and this portion is here. 7 million on the stack. Now, begin is just a 4th word, it's just a label in our code. So 1 minus dub. Now we have a counter and copy of our counter. And until is, in reality, it is if, but jumping to backward, right? So again, we're placing our seed for literal, and we need to go to this line. This is our 1. So 7 millions ends here. Begin will mark this address, and we will jump to this line again. Okay, discard our counter. It's done. And return. So this is cell number 20, and before we are jumping to 21. Okay, our main program. Why 10? We need to imagine any address of our LEDs. So this is output register number 10. Again, we can change it, we can modify and place our IO map at any position we want. Okay, okay, 0, dub, seed and 0, place it to port 1 plus, and go to 6 by 6 because our subrouting with delay starts with 6. Okay, jumping to 22. We can describe a test bench. What is a test bench file? And in reality, both VHDL and Verilog are simulating language, but they have synthesized subset. So not every line from Verilog is converted to hardware. Most of Verilog commands are describing input stimulus. So we can imagine a large box. We will give our board. This is our FPGA with inputs and outputs. And very commonly use it as a unit under test. And UUT is a common shortcut for the synthesized model. So when we take our FPGA with our project, we have input signals, and we need to apply our stimulus to see what happens. And a simulation software will show outputs. Of course, they can describe adder. They can describe stack. They can describe, I don't know what else. And this is very boring. Because, okay, we have our adder working. How we can check our CPU is working. So system level modeling is a high level of modeling. We are not checking every component. It's unit testing is very good as well. Okay. But in system level, we are filling our memory with program, with real content. We are applying clock signal. We are providing reset at startup. And we just run simulation and it will show what happens in our design. Okay. This is a full listing of our test bench. So we need to provide internal signals for our box. Just we can imagine our test bench as a very, very large box. No external signals, only internal to connect our board. We have clock input, we have reset, we have UART. We need UART to provide interface to our memory to prevent optimizing. Yes, it's UART. I will show it later. You will see. And we have 4 switches on our board, and we have 4 LEDs. Okay. We're taking our sound CPU core Verilog. This is name of our Verilog file in our project. Simulation will find it. Okay. We describe instance UUT. It's commonly. And we are connecting. Clock in our signal, we will connect to clock in of our CPU, and so on, so on, so on. There are no restrictions. We can name signals just like our signals of design looks like. So initial will performing once, no UART, no switches, reset state for clock, 1 for reset, and after 20 nanoseconds, we will assert reset. Okay, this one time, this is startup code. And forever, every 5 nanoseconds, we will invert our clock signal. So we can describe very easy forever lasting sequential clock signal for our project. Okay. Okay, what we have now? I have this simulation running and I replace delay counter from 7 million to only 2 iterations. Let's look how it works. Clock signal, reset. And it is going, PC is 0, okay, new PC is 1. It's easy because as default, we are trying to read command from the next. Okay, 21, it's our startup code. And command is jump. Yes, 32 is jump. And we can see state is 0 because we are jumping. Next command will not be executed. We will wait. We will wait 1 cycle to read proper value from the address number 22. And we can see, for example, okay, stick A, stick B. This is a code for return. And we can, this is signal to write number to LED port, and we can see 0, 1, 2, and so on, so on, so on. Okay.
Amazing.
Okay. Okay, okay. I'm plugging in my FPGA board.
Guys, I must say this is a dream for me come true. And thank you, Ilya, you are fantastic.
Wait. I have some more slides. Right. Well,
It must be Windows. Don't worry.
That always happens when you want to demo something.
No kidding.
it's USB cable.
Another in the meantime, another point. We are all
30 seconds. 30 seconds, please.
Learning how to interact with this new technology, with this Zoom technology. And the group, the Facebook group we have founded, is the same. We are trying to interact in a new world for all of us internationally. And we must learn from each other how to communicate better and exchange during this meeting and every time. This is not a video. This is a living conference, so you can make questions. This is the point, because I can watch a video of Ilya on YouTube, but this is not live, it's dead. And this is what we need to learn, how to communicate between us and make these conferences always better.
Yeah, good point. The only thing I would say is, you know, we have so many people on it. If we all start asking him questions during his presentation, it'll get him off, you know.
Oh, I cannot connect to. Connected.
The good thing about this is, give it 2 or so more conferences, everybody will be inherently familiar with the key combination to mute themselves in a hurry, and this will be much smoother.
Ilya? I'm trying to connect my board. It don't want. Okay, local. Connected. Open target. What's wrong?
Is it possible to reconnect it under a different COM port under Windows, which is very common?
Yes, I'm trying.
Don't worry.
Yeah,
good luck.
I think, you know, you're designing a very complicated computer. And it incidentally executes some false words, but the design is really too complicated. I would hope that you look at the EP32 design, which I think is available on the on the forth.org.
On SVFIG, Dr. Ting, it's available.
Yes, yes.
On the page.
I think you need to look at that because your design is.
Try to rerun my Vivado. Okay, while it's loading, our next steps. We can replace return register to return stack. So we need to add return depth register. We need to choose component. Some permissions are needed. We have flip-flops in FPGA. This is just registers of every logic cell. We have distributed memory in lookup tables, but this is Xilinx feature. This is Xilinx feature. It's not available for most of our. Okay, let's try. No, it don't want. No, it don't want to use it too. And I check it before it works. Please, don't want to start. And maybe with Digilent, no devices connected. No devices. Wow.
Could that be the USB cable? Because with these.
Yes, I just tried 2 USB cables and different ports.
Because with these USB cables, they use this tiny form factor they often use for phones. I have had so many problems with these things, with Raspberry Pis powering them. It's not even funny anymore. I seem to go through them quickly, despite the fact that they're not being moved. These things die too fast.
Okay. I will write video. I will record video and send to everyone.
Of course, Ilya, no problem. No problem with that.
Okay.
We make other classes also, no problem.
So we can use sharing block memory or maybe dedicated block memory. Dedicated block memory is a great wasting of resources because current 7 series FPGA has about 36 kilobits of memory for each block. It's a real wasting of resources. We don't need 1,000 subroutine calls. Maybe sharing block RAM. Okay, but we will need several cycles for fetching return address. We will use the same word for fetch data from block memory, and we'll decide is it to place on the stack or to use as return address. There are many trade-offs. What we can use in our design. Of course, more comments. We have micro architecture. We have fetch, execute, fetch, execute, fetch, execute, and we have a structure with registers. We can fit this structure with our own comments if comments are fitted in our structure, of course. So we cannot add another cycles. We cannot describe comments with electrical conflicts. So no writers from several sources to one register. If we inside these rules, we can imagine. We can imagine. We can think about commands. We need to implement our commands. Okay, this is single core project. So CPU and peripherals. Outputs of FPGA are UART, switches, and LEDs. We can convert it to CPU core with address, data, write to IO flag, and input data. There are many ways to use UART to download program. We use several internal formats, but I don't want to standardize it. This is very simple. This is very simple. For example, okay, this is our Sun CPU. A small list of commands supported. Our initialization, and very simple finite state machine for UART. At the end, we will increment program counter and write data, and RX data is filled from UART. So everything we will send to UART will be written to our program memory. This is very simple, and counter is resetting by the button on our board. I don't know. This is not too convenient, of course, because we need to press button every time. But I just don't want to force others to use our internal formats. It's something more complex. We have our internal protocol to describe which core we want to use. We can use several cores up to 16. And this is very simple. 4 bits is address of register, and 4 bits are data for register. So high bits, low bits. 16 register, 4 bits each. And we can connect it to second port of program memory. So this is code. I showed it before. Less than 300 lines of Verilog code. Usually our CPUs are about 1,000 lines, but there are no specific tricks here. Okay, our command list is short enough to perform LED counting. This is very easy. What about project summary? Less than 2% of FPGA. We can, oh no, there are no implementation here. Okay, so return to here. A question. Why we just designed for CPU? Not because we are Ford fans, and not because our FPGA CPU running at maybe 15, maybe 100. Indeed, this design is slightly less than 100 megahertz as default in Arctic 7 FPGA. But playing with synthesizer strategies, we can achieve 100 megahertz. If we are ready to rise our implementing time maybe 2 times, maybe 3 times, it's more complex process when compiling. So when we force CRD2, okay, we need 100 megahertz. Let's try, let's do it. We will achieve 100, no problem. If we will use, for example, ARM Cortex-M, when running Ford primitives, ARM has no stack. ARM has no hardware support of stack. It will emulate stack by its own command set. It will be slower, okay. If we will use C or C++ compiler, or even assembler, I think ARM will be faster. So why do we need Ford CPU? Example 1. FPGA is a very high performance hardware platform. It may implement, for example, fast Fourier transform, finite impulse response filter, video processing core, and maybe something else. Okay, let's add ARM-like CPU. Xilinx has Zynq series with hardware ARM inside. We will start to think about DDR3, about operating system, about drivers, and so on, so on, so on. How much attention we may pay to our hardware costs? I think less. So if we will add 4 CPU, it has small memory footprint. It has very tightly coupled system bus. No clock frequency lowering when working with distant peripheral. We can add custom commands. And at last, Ford cross compiler is easy enough to write. We can try. We can add command, describe it in Verilog, and add it to our compiler right now in several minutes. No problem. Just defining. Just Ford primitive, code for it. Ford primitive, code for it. We add new command. We will add a new Ford word to provide a cross compilation for our new command. Okay. Motors, robots, CNC machines, and so on, so on. Many processes, many axes, many legs or wheels, or I don't know what else. With only one CPU, we are forcing our software designer to do very hard work. Any overtasks must be checked. Is it break or not our previous written code? How we need, how we can switch, split our CPU time between our tasks? This is very risky and this is hard, and this will last for entire project life. Any new functionality means new time slots inside our main loop. This is dangerous. Okay, CPU 1, CPU 2, CPU 3 for every motor connected. Maybe CPU 4 for peripheral. Maybe CPU 5 for slow peripheral or for fast peripheral. I don't know. It's up on you. So CPU performance is not a key feature. We need to check this is role of CPU in our complete design. So what we can modify? Stack resources. Place small stack into flip-flops. This is very fast. Place medium size up to maybe 100 or 200 cells in distributed memory. Place large stack in block memory. Common fit, 8 bits, 6 bit, 36 bits because block RAM is native has 36 bits wide at output. 4 bits for operand designation for some kind of flag, and 32 for literal. If we will use our program very heavy dependent on literals. So numbers, addresses on the stack, addresses on ports, data to ports. Why we are limited to 8 bits? 32, 36, no problem. No problem. Please take a look on this. Take a look on this. No restrictions. 7 and 0, 31 and 0, no restrictions here. Verilog will support any real width of data. No problem. Cost optimized portfolio. So there are current view of Xilinx chips. We have Arctic 7 with 35,000 of logic cells. This is not maximum size. We have, for example, block memory, megabits and up to 13 megabits. We can place very serious software design into our FPGA with system on chip class device. And small memory for footprint means our program will be really serious. Ethernet, for example, very light, not complete Ethernet, not Ethernet, internet browser, of course, but very serious Ethernet. DSP, this is hardware blocks, hundreds blocks. For example, for FFT, for spectrum analyzer, for wavelet analysis, for filters, for I don't know what else. 100 megahertz to 100 megahertz, it's more performance than Intel Core i7. And fourth is not to stay between input and output. Fourth is to control our hardware cores. Very small. Okay, small box with spectrum analyzer. It's mass collectivity and is with Wi-Fi interface. So mass collectivity can be measured in real time. This is wrong way. It's it's my teaching. So when I'm trying to perform it right way, I'm very relaxed. And I can control it. All of this, okay, all of this, is a result of spectrum analyzing. It's not just ADC. It's spectrum analyzing in Spartan 7 FPGA with 4 CPU, collecting data from several channels and dealing with Wi-Fi model. Battery power. That's all. This is our latest design. So, okay. And the sky isn't the limit. We can write forth. We can design our CPU. We can design hardware accelerators. With Ford, and the sky is only the sky is the limit. With FPGA and hardware and software co-design, with Ford base, sky isn't the limit. Okay, thank you. Questions?
Excellent, Ilya, excellent.
Ilya, thank you.
That was fantastic.
Ilya, I have a question. When you turn off the power to the unit, does it forget the program? Do you have to reload it again? Like with Arduino, you can flash it and then it'll run. With this FPGA, do you have to?
Yes, FPGA boards has SPI flash connector. Oh, so of course, we can create bit file. We can use Vivado tools to download it, and we can prepare the same bit file and load it into SPI flash. That's easy.
Ilya,
it's very cheap.
Ilya, can you stop sharing the screen?
Oh, okay. Okay. Okay.
Thank you.
One of the things that I like about Lattice FPGAs, if they have the flash memory built inside, so it loads instantly, no waiting, hesitating while the FPGA comes up to speed. So no big deal, but I like that whole idea of simplicity. No ROM on the board, not necessary. It's built in the device.
Yes, it's Xilinx. It's obsolete series. It's Spartan 3AN with flash inside, but it's not the flash at the same chip. It's flash in the same package. So it just Atmel, or maybe I don't know exactly what is flash manufacturer, but it's 2 chips in one package. But now any kind of serial flash may be used to download the FPGA bitstream, so it's cost of SPI flash external is less than cost of FPGA.
Yeah,
so
I was talking of Lattice. The Lattice brand, this little guy right there, there's no EEPROM in there because it's built inside the FPGA.
Oh, yes, yes.
There's no loading. It's always there, so the instant you turn it on, it goes.
Yes, it's very
just a little thing, but I like that.
Microsemi Igloo. Look at Microsemi Igloo.
I do have this little guy for bigger projects.
Yeah.
35,000 LUTs. So you can do something pretty sizable with that.
So what I really like about the idea of Forth on an FPGA is you can extend, which is what Forth is all about, but you can extend the opcodes of Forth, and you could put Verilog processing, right? And Forth just calls an opcode that maybe loads let's just say some shared registers that are the input data, and as a shared register result, and then you could write in Verilog some sort of, like an FFT or some really heavy math code, and now you've extended the Forth language, to these super high level functions, and they're going to be running at the speed of silicon. They're not going to be running like they were running on a sequential processor, because Verilog will build, exactly that hardware engine to do whatever you're coding. So I could just see this as being way faster than, for example, putting a processor core in there and then writing stuff in C.
Yeah, and I know you've shown interest before. Some FPGAs are radiation hardened and rated for space. So
I'm designing with the RTG4 right now.
So yeah, you can go anywhere.
I know memory footprint. I know memory size. It's very important for radiation hard and for space applications, because memory is very vulnerable to radiation.
Right.
Smaller memory, easy to protect.
That was fabulous. I so enjoyed that.
Adrian was talking before the class of Ilya. I don't know, Adrian, if you are there.
I am indeed. I am here. Yeah. And if I take it out of the packet again, it's there somewhere. Tiny FPGA, probably quite limited, but it's a good start. Fits into a USB port, and that's it. Simple.
Brain, you don't have the video. Will you please turn on your video?
Well, at last it starts. I just tried it.
Oh,
please.
All right.
Can you see?
Yes. Looks great.
So just a binary count.
So it looks like FPGAs have this built-in stress detection system that makes them fail under pressure.
Yeah, the one you were talking about earlier.
Yep. Confirms my hypothesis.
Yeah, definitely in there.
It must be Chinese.
We need very good USB cables. This is why we are going to Bluetooth and Wi-Fi for now.
I was just going to say, I have a heap of wired boards here, and of the 3 USB ports on it, 2 have been permanently wired. One by actually chopping off the cable and wiring the 4 wires to the pads, and the other one by just hot glue gun. melt on it. So this is a known problem.
I like the idea. Hot glue gun, that's so duct tape. I love it.
Can I show you my rat's nest here? This hot glue gun is an integral part of it. I don't know if you can see it. I don't have a camera that I can take off. Bring it a bit closer. So, actually, I should handle it with care. I don't want any wires to come off. It's, but it's the only way to solve loose USB cables.
A question in the chat about my board. Yes, am I right?
It's upside down.
Yeah. Just show us. You want to see it blinking? That's all. Yeah, please. We'd like to see it blinking.
Yeah. Sorry.
Yeah. Just hold on there. Yeah. Just let us see it blink. Thank you.
Talk, Ilya, so that you become the master of the camera. Talk, Ilya.
Ilya, I think your design is a very complicated CPU. It's register-based and it's very inefficient. Please take a look at the EP32, in which I have solved many of your problems. There's no need of pipelining. The stack problem was solved, okay? So please do look at that design, and you can do it much faster and much simpler.
I have 8 generations of stack CPU. They are different. This is the simplest one. I use it and I test this approach with my students. This is the simplest one we can implement. All over are focused on targeting proper FPGA resources. We can use distributed memory or effective or not tricks around dual port block memory. But this is more complicated. When we write Verilog code this way, we let the synthesizer to decide how to implement it. This is why I describe only 8 cells of a stack. We have CPUs, for example, from 300 cells to 2,000 cells. It's not a CPU design problem. It's a system design problem. We can focus on performance. We can focus on data bandwidth. We can focus on tightly coupled with peripherals or not. Our previous project, okay, I can see this in our chat. Paul Richter is one of our key customers. He lives in Russia, but has a business in USA. And he ordered several thousand devices. Of course, BOM is very critical. So we pay great attention to make it as low price as we can. As low price as we can. And of course, from the scientific point of view, we need to know how to create performance, how to create low power, how to create very compact CPU design. But all of this is for optimizing up to customers' goal. If customer asking for very high performance, okay, let it be very high performance. If customer is asking for very compact, okay, it will be very compact. But we cannot dream on the way. We need to research it first and suggest architectures we can use in reality. So, of course, I know this is very simple, but my web purpose, please check the second slide of this presentation. My purpose is to explain, not to create performance, not to achieve compactness. In this way, I will promote myself. This is not my goal. My goal is to launch processes of CPU designing for all meeting participants. So this is my gift to Ford community.
Bravo, bravo. Very good. Excellent. We enjoy it a lot, Ilya. It's incredible. It's my dream. I follow Dr. Ting, I follow Don, I follow Ulrich Hofmann is now with us. It's another dream come true. And everybody in the Ford community. And I live very, very far away from the development countries. We are in South America. And because of my work, I had other things to do in life and I could not follow Fords. I stopped for a couple of years. And when I went back, one of my dreams was to program the, where is it? Here. The FPGA. Oh. This is a chip board. No, this is a chip board.
Cyclone 4, it can be used also. It's Altera. It's Altera. One generation before. Yes. Spartan 6 is 65 nanometers, as I remember.
My purpose is as hobbyist. And so now I thank you very much because I can follow your class. And I will test also of Dr. Ting. The EP32, everybody. I will test everything.
So my objective is not to count followers. My objective is to count people who will design its own CPUs.
Yeah, this has been a great seed. I can see using both what you've done and what Dr. Ting's done. Dr. Ting, you did it in VHDL, didn't you? Not Verilog.
Not VHDL, yes.
Yeah, yeah. So it would be, I think it'd be interesting to convert your code to Verilog. Then you could kind of match the codes a little easier. You know, 20 years ago, VHDL was the language to use. Today, Verilog is really kind of taken over, I think.
Yeah, not so much in Europe.
I know both. Well, Europe is really big VHDL, right?
Mm-hmm.
Yeah, but yeah. So I know both languages, and you do a lot less typing with Verilog. I'd say.
For sure.
VHDL is more convenient to me just because of many checking at synthesized stage.
Well, you know,
we can achieve the same results both in Verilog and VHDL just to some conversions of code. It's not a problem. Indeed.
Well, back in the day, like in the 90s, the ASIC guys liked Verilog because there was a lot more tighter timing stuff in the Verilog language. You could control the timing to a gnat's ass, and VHDL didn't quite have that. So VHDL was used on FPGAs in the 90s and beyond, and then Verilog was the ASIC guys love Verilog, and they always use that from a historical standpoint.
Indeed, in Vivado we can mix language for different models. It's not a problem. It's a mixed design flow. There are no separate licenses for VHDL or Verilog.
Yeah, as a funny note, in the 90s I took an FPGA class and I wrote my own fourth processor in VHDL, but I used behavioral VHDL, and I never got it running. It was for a class, and it was my homework, and I just wrote the code and handed it in. But
yes, from my experience, I can remember some groups of engineers for Xilinx courses. And listeners who started from VHDL. After that, they're coming to me for Verilog. As an official Xilinx trainer, I provide lectures for Xilinx materials. And okay, Verilog, so simple after VHDL. And Verilog and VHDL, it's two stages. It's two stages. First of all, it's to switch from software to RTL design. And second step, it switches to more complex and more strict VHDL. When people are jumping to VHDL, okay, there are rules, we need to learn it, no problem. And Verilog is just more flexible language, but some tricks are hides inside. We can achieve side effects. For example, very simple, different signal bus width. No problem in Verilog, it's filled by zeros or just truncated. But VHDL, okay, 16 bits to 32, not, this is an error, you can fix it. You need to fix. Okay, so it's some kind of architectural discipline. We need to think it's very strict and synthesizers will check it. I think it's not a problem. Not a problem for teaching materials about architecture. 6%, I don't know why 6%, maybe it's some magic number. To write code, to debug, it's 6% of project time and expenses. First, we need to do is to think about system design, to think about setup environment, to think how we connect with, how we split our task between hardware and software, and how we will go to customer and show what we can. How large is FPGA? What is our clock speed? Who cares? Who cares? The right way is to not to choose way leading to success. It's to make the situation so always will lead to success. And this is system level design. This is architectural design. I don't want to provide tricks with Verilog. We have fetch, execute, fetch, execute, fetch, execute. This is simple. This is simple. While we are staying inside this micro architecture, we can provide 4 CPU, C CPU, register level CPU, and so on, so on, so on, so on. If we face any kind of problem, resource, performance, bus width, signal complexity, ROM complexity, okay, we are returning back to architectural stage and trying to select another architecture. This is what we need to do. This is what we need to do. Sorry, just I'm professor. I just to switch to my typical work.
This is a must-get book. This one here. This is 2017. The author of the book, you know, Stuart Sutherland, was on the 2017 Verilog standards team, and it's an excellent book on system Verilog. So, in case not everyone understands it, so with Verilog and you have Verilog and you have system Verilog. System Verilog is more like C. You can use structs. You can use array. I've actually tested this. You can use arrays of structs. You can do some really wild stuff with system Verilog. And same thing with behavioral VHDL, I might add. But these are, you're using these languages at a more higher algorithmic level than the bit banging of, you know, just straight Verilog of like 2000, you know, when we're just basically, you know, doing bit stuff. So that's an excellent book. If anyone really wants to see the full power of system Verilog. That was fantastic, Ilya. It's great.
Okay, I forgot to say how the name sun is appearing. Our previous meeting was with Peter's word. We will follow the sun in our schedule. From Australia to, okay, sun is very good example. It's independent and this is for everyone.
There you go.
Yeah.
Okay, so more questions?
That's it for me.
Available.
I'm anxious to
I had a
download your code.
generic question. I had a generic question. In designing CPUs, there's many ways to go about it. And I've been looking at where you use wide instruction words and encode the bits that control the internal units of the CPU as bits on that word, so that it's rather easy to include multiple instructions in one, because if the timing allows it, you can take an address and put it out to the address bus and take the top of stack and push it, and you can do all sorts of things simultaneously.
I can tell. I think a month or two, my PhD student will be on our dissertation council. He's very, his expert level in compilers is very high. He can write C2 compiler, and he did this to analyze how we can use several data paths. Of course, inside FPGA, we can use very high bandwidth, but it's a fundamental problem, data path magic. For example, we have 2 commands. We can run it in parallel. We can 3 commands in sequence. We cannot divide our clock cycles by 2. We will use 2 commands and 1 command. And just imagine a very, very complex equation tree. It has a root. We need to combine all our operations together, and at the last stage, we must use only 1 command. So, of course, we can place in the FPGA many arithmetical logical units and very wide command, many operands, many register files, many stacks. We need to find a way to support it in compiler. We need to write compiler first. And we are returning back to system level design. If we have this kind of software, okay, it will work. If we're starting with schematic, no, please. After several months or weeks, we will start to search for customer. And we will start to improve our design, to find ways to add command, delete command to fit in our memory. And this is, I think, this is a good exercise. This is a good exercise, again, as a previous question. It is very good to know how to build very local extrusion word CPU with many data paths. It's very good to understand how we can place it into FPGA, how we can do floor planning, and how we can provide multiplexers between data paths. But after all of this, we need to look at the architectural level, on our typical algorithms, and maybe delete some useless features from our CPU. This is not a FPGA way because, for example, Intel or AMD or ARM must rely on a massive market with millions of users. They design a general purpose CPU. With FPGA, we can create a CPU for specific task. Okay, we have our portfolio, we have our architectures, we have designs, we have parameterized design because 32 or maybe 64 or 16 and how many memory and multiplier inside and maybe multiply and accumulate, for example, for software defining radio. It's very useful. We have all of this. What is our task? We can modify existing architecture or try to create a new one. So very long instruction word is very good. If we can split our activity between researching and providing a design for future and providing a solution for existing task. It's very good. It's like to tune a radio receiver with two tunes. It's nearly impossible. We need to use one thing, one widget to search proper frequency. We cannot, in reality, we cannot research and solve engineering task.
Yeah, if you want to know more about that, look at Chuck Moore's patent on the Shaboom processor and the Novix, because he uses multiple. He only had 25 core fourth words, and so that's only 5 bits. And so he could actually have data and code words and multiple code words in the same. It's 32-bit wide, but you could have like a 16-bit data and then 3 code words. You know, if you look at
I know.
Right.
I have seen it and I study this, and we have found it, and he is absent now, but officially he's my PhD student. It's not a young boy indeed. He's very experienced. He has a first Green Array CPU in Russia. He works for Green Arrays, he works for Intellisys with 24 cores for CPU, with 4 cores, and he writes simulation software, and he digs deeply into compiler, and he is trying to write a C compiler to Ford. Wow. And many things. It's obvious for hardware engineer, but this is a real problem. How to inspect code, to identify pieces of code which can be converted to assembler codes. We will use hand programming in machine codes. If we want to jump from a high-level language to machine code, we need to understand what steps we are performing in front-end compiler, and what is our internal representation. If our internal representation of program very good fitted and aligned with our hardware, backend will be easy. It will be obvious. It's what Microsoft did with .NET. It's very explicitly highlighted Microsoft intermediate language. It's stack machine. It's stack machine. Stack machine and stack representation. It's very good and very good known internal representation of many high-level language. So we can compile into stack representation and use Ford machine. We can compile into a different representation and use accordingly designed machine. Ford, it's easy both for software designer, both for compiler designer and FPGA designer. We can combine it into one person indeed. It's very hard for C compiler. It's C compiler specialist. It's all the time to research, all the time to study compiler articles, compiler materials, and no time to be an electronic engineer. This is what we can found. This is a great benefit of for. We can combine electronic engineer, system programming, and application programming, and use high-level language directly translated to machine codes. This is very good.
I have one comment about the multiple instructions. Wait, you know, this thing's going to run at 50 million instructions per second. You don't really need to go that far to do the multiple instructions. I'm a KISS guy, you know, keep it simple, stupid. So I like your simple architecture, you know, and I don't see any reason to go to multiple instructions, but the other guy was interested in multiple instructions, so I thought I'd throw that out there. But, you know, I like simple.
I will prepare, maybe not to November. I will prepare very long instruction word CPU design and will show it in my optics board. No problem.
Cool.